Alright, so in this lesson we're going to look at what's called the LC circuit, which is a circuit that contains a capacitor and an inductor. Now, for the sake of simplifying this circuit to analyze it, I've removed any batteries or any power sources from the circuit, and we're going to say that we start with a fully charged capacitor and look what happens as that capacitor discharges in this circuit. So where we really start is right over here. And so capacitor's fully charged. All of the energy in the circuit is electrical energy at this point, and the current is zero. Well, what happens the moment this situation occurs is that current starts to flow this way. The capacitor starts to discharge. So the current starts to change. What that does is it induces a magnetic field in a way that opposes that change in current. And so we'll get to some point in between there where the energy is equally distributed. What's going to be true at this point is that current is going to be maximum at this point. Or excuse me, no. We're going to be halfway to maximum current. When we get to this point, the capacitor is fully discharged. So now the current is now a maximum value this way. Well, of course, all of the energy is now stored in the magnetic field. Of course, the current can't go to zero instantaneously. So the inductor continues to induce a magnetic field to keep current going in that direction, which starts to build up charges on the opposite side of the capacitor. And so what ends up happening is that the capacitor gets charged in the reverse orientation. Current goes to zero, capacitor gets charged in the reverse orientation. Again, all electrical energy. Capacitor starts to discharge. In this case, current goes counterclockwise or clockwise. We end up with the point where capacitor is fully discharged. Inductor has maximum amount of voltage in it, so dIdt is maximized. We're also at our dIdt is we're at a maximum current at that point. We then end up with the next stage. Capacitor starts to charge because the current can't go to zero instantaneously, and we end up back where we started. So this really looks like a trade-off between all energy in the capacitor, all energy in the inductor, all energy in capacitor, all energy in inductor. So capacitor charged one direction, current flows counterclockwise, current goes to a maximum, capacitor begins to charge the other direction, capacitor fully charged the other direction, current goes to zero, capacitor begins to discharge, maximum current in the clockwise direction, capacitor begins to charge in the original direction, capacitor fully charged, current is zero. So let's look at this system mathematically and look at what's actually happening. So here we have di over dt. If we actually work out what Kirchhoff's rule looks like, L times di dt plus 1 over c times q. Well, it's worth pointing out I is the derivative of q, so really di over dt is d squared q over dt squared, or the second derivative of q. And so if we work this out, what we see is we get a differential equation where the second derivative is equal to negative the function. Well, guess what? There are two functions that fit that, and those are sine and cosine. And so really what Q looks like in this case is I put capital Q, the maximum charge on the capacitor, times cosine of omega t plus phi. And so if we look at what some of these values are, omega is related to frequency, how quickly does this charging, discharging happen, and phi just basically shifts the function right or left. Now it happens to work out omega, the angular frequency, is related to L and C, 1 over LC, or 1 over the square root of LC is omega. How we can get this value of omega is by looking at other types of systems that look like this, say the spring mass or the pendulum, and apply what we already know. This is essentially a type of simple harmonic motion. Now if we look at the current, what we see is take the derivative of this, we get a current that looks like that function there as we work this out. And so it becomes pretty clear that when charge is zero, current would be maximized. When current is zero, charge would be maximized. So where do we use LC circuits? Here's a good example of one that we would use an LC circuit for. Say I want some help designing an LC circuit to pick up an AM radio frequency of 1020 kilohertz. So 1020, so what's true about AM radio is that in AM radio there's a carrier wave of a particular frequency, and all of the information is carried in modulating the amplitude of that carrier wave. So what's true about AM radio is that the frequency of the radio wave is constant, and that all the sound that gets carried is just by modifying how big that wave is. If you think about that for a second, pretty cool if you really think about that, that you can basically create a device to pick up these AM radio signals, and it's not that difficult. All you need is a speaker, a capacitor, and an inductor, and you can do this. So what is the value of the inductance that I should look for? What I'm looking for is an LC circuit that has a frequency of this oscillation that's equal to my AM radio frequency. What's going to happen is then my AM radio frequency can then be a voltage source, because the energy carried in that radio wave can actually then drive my simple harmonic motion in my LC circuit. So what I want to do first is figure out, well, how do I actually convert frequency into things that are useful? And the thing to remember about angular frequency is that it's 2 pi times frequency. So really 2 pi times this frequency, 1020 kilohertz, should be equal to the square root of 1 over LC. Well, we can actually then solve out for L, take and multiply all that out, multiply by L to get it over on the other side, and we can then divide things out to get L by itself, and we get 6.12 times 10 to the negative 4th henries, or 61.2 microhenries. Wait a second. Should be 612 microhenries, I think, since micro should be times 10 to the negative 6th. So I think I got this wrong. I think it's 612 microhenries. So if I had this inductor of 612 microhenries and this 250 picofarad capacitor, I could connect them together with some string or some wire, plug a speaker into that, and I could actually pick up radio frequencies of 1020 kilohertz. It's worth pointing out that you can also create a radio wave this way as well. By driving a current through an LC circuit, you can actually create radio waves as well. That this magnetic field induced by the inductor helps create the radio wave, and it's really the inductor that's picking up the radio wave. We'll talk about that a little bit more when we talk about Maxwell's equations and how that works. So let's say we have a oscillating LC circuit made of a 250 millihenry inductor, or 75 millihenry inductor, and a 3.6 microfarad capacitor. And we want to know if the maximum charge on the capacitor is 2.9 microcoulombs. We want to calculate the total energy in the circuit and the maximum current. Well, the easiest way to calculate total energy in the circuit would be to figure out, well, what happens if the capacitor is fully charged? Well, the voltage would be Q over C, right? So if we plug that in, we get Q squared over 2C, and so the charge stored by the maximum charge stored by the capacitor is 1.17 microjoules. If we wanted to figure out maximum current, well, it's worth pointing out the maximum current and maximum charge are related to one another by this factor omega. And so if we actually calculate out omega, we can find the maximum current is 5.57 milliamps for this particular circuit. So those are a couple quick things we can do with LC circuits. And what happens if we have a capacitor and an inductor connected to each other.